Assignment 4, Existence Theorem. This is very important theorem. So the existence theorem says, let V be a finite dimensional vector space over the field F and let dimension of V is equal to n. Right? Then a linearly independent set with n elements is a basis for V. What we have to do is, it is given to us that V is finite dimensional vector space, right? And dimension of V is equal to n, which means the basis for V has number of elements equal to n, right? So first we will show that the vectors more than n present in V cannot span V, or the vectors more than n are linearly dependent. This we will show first, and then we will use this result to show further that if we suppose any linearly independent set of n vectors in V, then we have to prove that that linearly independent set forms the basis for V. So we will use this that result in proving this result. Right? Let's start with the proof. Now since the dimension of V is equal to n, this is given to us. Now because dimension of V is equal to n, let's suppose the basis for V to be as V1, V2, V3 up to Vn, right? Having the number of vectors n. So these are the bases, and I have to prove that first every set of vectors in V which contains more than n vectors is linearly dependent, because the basis for V are n in number, which means we have n linearly independent vectors. But if I increase this number more than n, then that set of vectors should be linearly dependent. First we will show this, and we will use this result in the further proof. So suppose this is your vector space V, and it is having orange colored vectors as total number in n, and then I have added more vectors, the green colored one, and total green colored one plus orange colored one. These whole set of vectors are suppose m numbers, and this m is greater than n. Right? So let any m vectors in V are W1, W2, W3 up to Wm, where m is greater than n, and we will show that this set of vectors are linearly dependent, okay, because these are greater than n. Now since Wj, any Wj from these vectors belongs to V, for all j going from 1, 2, 3 up to m, fine, and V is equal to V1, V2, V3 up to Vn as the generators of V, because it is given to us that dimension of V is n, and we have chosen V1, V2, V3 to be the basis for V. So there exist scalars for that specific Wj, and I named them alpha 1j, alpha 2j, alpha 3j up to alpha nj. Why n? Because first scalar is for V1, second is for V2, third is for V3, and last one is for Vn. So we have to write down the linear combinations with these vectors, right? So Wj is present in V, and because this is a generating set, so every element of V is a linear combinations of these vectors present in the generating set. This is that definition. So Wj is equal to alpha 1j V1 plus alpha 2j V2 plus so on alpha nj Vn. So this is equal to the summation, and summation is on I going from 1 to n, right? And this is alpha ij Vi. I is on V. V1, V2, V3, Vn, I suppose that as I. So marking this as 1. Now required to prove that these are linearly dependent, right? For that, let's choose C1, C2, Cm to be the scalars, and I'm writing the linear combinations. So let C1 W1 plus C2 W2 plus C3 W3 up to Cm Wm. This is equal to 0, the linear combinations. And now taking the summation, let's say now J from 1 to M on Cj Wj equal to 0. Now from 1, putting the value of Wj over here, so I get summation j going from 1 to m, Cj, summation I going from 1 to n, alpha ij, Vi equal to 0. Okay, now taking the summation from I to 1 at the first place, because I need to get the set of homogeneous linear equations. So this implies summation I going from 1 to n, and summation j going from 1 to m, and alpha ij, Cj, collecting this, and at the last I'm having Vi, this is equal to 0. So this implies, now this is the set of linearly homogeneous equations. So writing these equations, homogeneous equations, equal to 0. So now this is equal to 0 and I is from 1 to n. This is a system of n homogeneous linear equations, right? N homogeneous linear equations in m variables. I always, every time I say that, Cj denotes the number of variables, right? So the system 2, marking the system as 2, system 2 has a non-trivial solution. This is a property that whenever you are having the number of equations, if less than number of variables, then the system has a non-trivial solution, which means not all C1, C2, Cm are 0. If these are not 0, which means W1, W2, W3, Wm are linearly dependent. This is the definition for linearly dependent. Scalar should not be all 0. So thus every set of vectors in V having more than n vectors are linearly dependent. Fine, marking this result as 3. This result is important to use further. Now to get the basis for V. Okay, it is now let's take, okay, first I will explain you this diagram. This is a vector space V, and I'm choosing U1, U2, the purple color elements, the number of elements n, and it is given to us that this set is linearly independent vectors in V. Okay, so if I'm having the linearly independent vectors in V, this forms the basis for V. This now is required to prove. So it is given to us, let's have a number of linearly independent vectors n, which is given to us. So I'm writing let U1, U2, U3 up to Un be the linearly independent set. This is given to us with number of elements n. And to prove that these forms a basis for V. Okay. So it is already given to us that this is linearly independent. For basis, two things are required. The vectors should be linearly independent, which is given to us. And second thing is, these are the generators for V. Okay, so required to prove that these are the generators for V. One thing is already given to us. Second thing we need to prove for basis. Let's take element U from V. Okay, so then if I see this collection U and U1, U2, U3, U4, Un, these are, yes, these are linearly dependent or linearly independent. Very good, these are linearly dependent. Why? Because of this property. Third, every set of vectors in V which contains more than n vectors are linearly dependent. Now these vectors are total in more than n in number, right? So I must write because these are more than n vectors, so these are linearly dependent. Fine. Okay. Because it is linearly dependent, so there exist scalars, say for u I'm taking alpha, for u1 I'm taking alpha 1, then alpha 2 up to alpha n. These scalars which belongs to f, not all 0 because these are linearly dependent, so we choose the scalars not all to be 0 such that alpha u plus alpha u1 plus alpha u2 up to alpha 1, alpha 2, alpha n un equal to 0. Marking this as 4. Okay. Now I have to claim that this alpha is non-zero. Okay, because this is linearly dependent. These vectors are linearly dependent as being more than n, which means the scalars I am taking. So I have to also show that not all the scalars are 0, which means I have to claim that this alpha, the extra one, this is non-zero. Right? We have to claim this? Okay. So claim alpha is non-zero. So if possible, suppose alpha is 0. What will happen then? Then from 4, if this alpha is 0, we get this thing to be equal to 0. So we get alpha 1 u1 plus alpha 2 u2 plus alpha 3 u3 up to alpha n un equal to 0. Okay. So this implies what? What happens to these scalars alpha 1, alpha 2, alpha 3? All are 0. Why? Because it is given to us that u1, u2, u3, un are linearly independent set. This is given to us. Okay. So, because u1, u2, u3, un are linearly independent, so alpha 1 equal to alpha 2 equal to alpha 3 all equal to 0. Reason given that u1, u2, un are linearly independent. Now if all these are equal to 0, then this alpha is also equal to 0, we have supposed, right? These are all 0 and we have also supposed that alpha is also 0, which means alpha is 0, alpha 1 is 0, alpha 2 is 0, which means u1, u2, un. These are linearly independent. Okay. So this implies because as alpha is 0, alpha 1, alpha 2, alpha 3, all the scalars are 0. What does this mean? This means, so u1, u2 up to un, these are linearly independent. My God, this is so much. This is a contradiction to third result. This is a contradiction to this third result, that every set of vectors in V which contains more than n vectors are linearly dependent. So these are more than n in number. So these are more than n in number. These are linearly independent, which is a contradiction. So this is a contradiction to third result. So our supposition was wrong. This supposition was wrong. So alpha should be non-zero. Okay, so we have claimed that alpha should be non-zero. Again from 4, if this is non-zero, let's take the remaining one to the right hand side. So alpha u is equal to negative of alpha 1 over, let's write first as negative of alpha u1 negative of alpha 2 u2, negative of alpha 3 u3 up to so on, negative of alpha n un. Fine. Now as alpha is non-zero, can I divide alpha all over? Yes. Can I divide? Yes. So alpha is equal to negative alpha, sorry, u is equal to, because I'm dividing alpha all over now, because I have claimed that this alpha is 0, sorry, I have claimed that this alpha is non-zero, then only I can divide. Okay, fine. So because alpha is non-zero, so I'm dividing all over alpha. This is u. Fine. This is what? What does this mean? That this u is this is a scalar in itself. This is also a scalar. This is also a scalar, right? If you name these scalars as beta 1 u1, beta 2 u2, beta n un, so which means u is a linear combinations of u1, u2 up to un. So u is a linear combinations of these vectors. U was arbitrary and u is also belonging to V, which means every element of V is a linear combinations of u1, u2, u3, un. This is what we need. If every element of V is the linear combinations of these, which means V is generated by u1, u2, un. Yes. Now since u1, u2, u3, un are linearly independent, which is already given to us, and we have proved that these are the generators for V, that is V is generated by u1, u2, u3 up to un. So both the conditions for bases are now proved or satisfied. So therefore u1, u2, u3, un forms bases for V. Fine. Okay, thank you so much. God bless.